welcome to everybody. I'm László Szentmiklósi from the Budapest Neutron Center, and this session will be dedicated to neutron imaging. I hope you all find your proper slots. And if you don't mind, I will start the lecture. Anytime, if you have questions or comments, please feel free to interrupt me and ask questions, either by the chat window or you can also ask. Okay. So this lab training will have two parts. The first part will be devoted to the presentation of an already taken experiment for dynamic radiography, where we will make a very simple experiment to check the water uptake of a pH paper. And this we will elaborate together. For this, I hope you did get some training materials from the organizers, namely two programs and a data set. Do you have them?
I think it was said that no program needed for this practical.
And so did you get the data or not?
No.
No. Do you want to practice yourself, or do you prefer to watch what I'm doing? Okay.
We got the studies on a solid and liquid state NMR practical solution data set from Pharma yesterday. And then, yeah, I think that's all, and that's not belonging to this lecture.
Okay, so then
and then we were also asked to download a few.
I sent you a link in the chat window where the entire thing can be downloaded. So either if you don't want to do it right now, then you can take it for later if you want to practice. And the program which corresponds to this can be downloaded from here. But even if you don't have these available, don't worry. I will have recorded videos, snapshots, so I will show everything what should be done, and later you can reproduce yourself with the given data set if you are interested. Okay, so and the second part of the lecture will be devoted to a demonstration of 3D volume rendering, and we will have a look at a tomography data set and see how we can visualize in 3D and what kind of tricks we can do with such data set. Okay. So just to present ourselves, we are the Budapest Neutron Center in Budapest, Hungary. We have a 10 megawatt research reactor, which is a Russian design, and around this research reactor we have quite a few, about 60 measurement stations, and two of them are dedicated for neutron imaging. We have RAD station, which is inside the reactor hole, which is right here. And we have the normal station, which is in the core neutron guide hole at the end of neutron guide number 3. And so these two imaging stations have differences in terms of field of view, spatial resolution, time resolution, and amenable, trans-illuminable size of samples. So they are very complementary to each other. And based on the exercise, what we need to do, we can choose one or the other experimental station. The technical background is as follows. So this is the radiography station. We have the neutron beam from the reactor, and this is not a guided beam of neutrons, but the neutrons just fly in the open air until the sample. And we have a downstream place detector which records the shadow image. The neutron flux is in the order of 10 to the 7, which means it's a medium flux facility. So it is applicable for most of the measurements, but if you need really high resolution, then this flux is not sufficient, and you should choose a detector system and a beam which allows higher spatial resolution. Besides neutron imaging, here we can also do X-ray imaging and also combine neutron and X-ray studies. This is partially possible even without touching or moving the sample. So we have the image detector system, which consists of a 5.5 megapixel camera, and with exchangeable scintillator plates, we can make it sensitive to either gamma rays or neutrons or X-rays. Sorry. So the lens and optics and the mirror and all this downstream part of the image detection are common, while exchanging the scintillator plate behind the sample, we can make the system sensitive to one or the other radiation modality. The scintillator screen for neutrons can consist of either lithium-6 fluoride embedded in zinc sulfide or gadolinium oxide, and these can convert the neutrons, or in case of gadox, the X-rays, to visible light photons, and these are registered by this SC camera. We have 3 commercially available optics, which are interchangeable, and by means of this, you can change the field of view. We can set a relatively large field of view with moderate resolution, or we can set a higher resolution, but with the expense of a reduced field of view. And so these are the typical spatial resolutions and the time resolutions available at RAD station. Sorry. This is the X-ray generator that we can install in place to the beam port, and this makes it possible to make dual imaging. This is the sketch of the normal station, where we use core neutrons to illuminate much smaller samples. So here the typical sample size is just a few centimeters, and we have almost the same amount of neutrons here, and the field of view is maximum 4 by 4 centimeters. And here we have I designed a feature of Pinhole Exchanger, which can help us to make compromises between spatial resolution and imaging time. Here you see 2 different pinholes, and in the background you see 2 black things. These are so-called graphite scatterers, which can be used to make the beam profile more homogeneous. Due to the properties of the neutron guide, the raw image after a neutron guide always shows some kind of stripe structure, but this is very unpleasant for imaging purposes. Or the goal is to have something like this, which is quite flat and smooth. And this one you can achieve by changing the collimator sizes and installing different thicknesses of graphite scatterers upstream into the beam. And why is this L over D ratio important? Because the best resolution is provided by a camera system if you put your object right next to the scintillator screen, so almost zero distance from the image detector. And as you go farther and farther away from your detector with your sample, the beam properties will become dominant in the image blurring. And if you have a very nice and parallel beam of neutrons, like in this case, then the contribution of neutrons to this blurring will be moderate, and there will be no significant difference between, let's say, the front side and the rear side of the object. While if you use a beam which is not so much parallelized, so this L over D ratio is lower, then the spatial resolution next to the camera and far away from the camera will significantly differ, and this will bring in some blurring in the final imaging result. So that's why this Pinhole Exchanger is very efficient in optimizing the beam properties to the requirements of the experiment. Of course, if you use a smaller pinhole, then you allow fewer neutrons to reach the sample, and as a consequence, you need longer exposure time, so you will lose time dynamics or time resolution. And this has to be always optimized case by case from experiment to experiment. Okay, I think that we covered already. So the station consists of this imaging camera, the sample chamber, this NIPS detector system for gamma spectroscopy, and the sample stage with X, Y, Z, and omega stages. So with this, we can freely manipulate our object within the sample chamber. And into this position, you can install a laser pointer, which helps you to position the sample properly within your sample chamber. This will be a video showing the facility first, and as you approach the beamline, you can identify the flight tube, the sample chamber, the beam dump, the neutron imaging camera, and the sample stage at the bottom. And here we have already prepared the experiment. So here is a little vial made of Teflon. Teflon is a nice material because it has very small shadow image in the image, so because it interacts weakly with the neutron beam. And this contains water, and some boric acid were added to improve the contrast. And up here you see a pH paper, and we gradually move this pot of water up until the water level would reach the bottom of this filter paper. And then the paper will start taking up water, and the water level will rise due to the capillary forces. And this added water content can be recorded with this neutron camera, and that will be the data set that we will evaluate. Okay. And now we can start taking images. Of course, we need to go away first and start the neutron beam. And usually in dynamic imaging, we take a series of images, so not only one of them, but you can set the acquisition system to take an image in every 5 seconds or 10 seconds. And then at the end of the experiment, you can download the entire set of images to your data acquisition computer. To process the data, we use typically this toolkit, which is called Fiji, and ImageJ. ImageJ is a freeware software, so everybody can download, and it has a very broad knowledge in the image processing, and it's customizable, so you can download plenty of plugins written by the community and install them. The whole thing is in Java, so you can even write the plugins yourself. And this will be the program that we will use for this demonstration. Actually, we need, for the data, we need not only the shadow images, but we need to acquire 2 additional correction image sets. One is so-called beam image or open beam image, which means you have to record the spatial resolution of the neutron beam without a sample. And the other thing what you need to correct is the dark image, which is the representation of the camera noise without any object and without any neutron beam. So these 2 corrections are required in order to carry out correction of the measured raw images. So the first thing is that in this ImageJ, we import the images, and we use a so-called image stack functionality. So with this, you can load all the 112 similar images and store them in a stack and scroll between them very easily. And the other fancy thing is that you can create mathematical operations, and then it will be carried through the entire stack. So you don't need to manipulate the images one by one, but you can treat them together. So this is the so-called stack functionality of 3G. If you have multiple kinds of images in one directory, then to this file name field, you should put something like BI or DI, which stands for the open beam image and dark image. Then the program will selectively load only those images where the file name meets this convention. So this way you can sort very nicely the images, even if they are located in one single folder. And here you can see some other technical details relevant for this experiment. So first, let us load all these images. So this is the beam image. So the distribution of the neutrons without any sample. And then we load the dark images, which is the noise distribution of the pixels. And then we load all the relevant shadow images for this water uptake experiment. And then the program will create you 3 image stacks. And for beam image and dark image, we also record several of them, up to 5, 10, 13, in order to have a statistically relevant data set. Then the next step, once we loaded the data, is image filtering. You can use quite a few very sophisticated image filtering techniques, and these are required either because there is noise, so you want to smooth the statistical fluctuation of your image, but more importantly, we should treat certain outliers that are there to bias the outcome of the experiment. So such outliers can come from the so-called dead pixels, when one pixel is malfunctioning and does not is not able to record the proper value of the information. So then it is either completely zero or completely full. So these dead pixels should be treated as an average of the neighboring pixels. The other typical source of outlier is gamma radiation, because even the neutron shields or neutron scintillator screens are to some extent sensitive to gammas. And if the gamma ray interacts with the scintillation screen, then it can oversaturate one pixel or a few pixels. And this also has to be corrected for. And in this program, there is a feature called remove outliers that we will use for this purpose. And you will see how it's going on. So in this feature, you can manipulate the brightness and contrast of the images without touching the numerical data. It is only relevant for the display, and you can change it anytime. And by increasing the lower or the upper or decreasing the upper end, you can enhance certain regions of the image where you want to focus. So if we are looking for oversaturated pixels, then of course we are interested in the higher end of the grayscale. So the lower end of the visibility threshold is increased, and what is left over is the high intensity region of the image. So here you can, with the mouse pointer, you can move to the proper pixel and see the values which are given over here at the upper panel. And here we can identify one outlier pixel, which is much more white than the neighboring pixels. And you can zoom in and out with the numerical plus and minus buttons of your keyboard. And we will optimize the image noise filtering or outlier filtering to get rid of such structures. So we choose the remove outliers feature. I'm sorry. Yeah, from here. And here you have two parameters to fine-tune. One is the so-called threshold, which distinguishes between useful and unuseful intensity, and the radius, how many neighboring pixels should the program average in order to have a better estimate instead of this white spot. You can switch on this preview functionality, so even if before you apply this filtering, you can see the outcome. And of course, the same procedure has to be applied to all data set for the shadow images and also for the beam images and dark images. And if we return to the position where we saw the outlier in previous times, we see that it disappeared, and what is left over are useful signals, and they are kept. So not all high intensity values are to be discarded. They are sometimes useful information and part of the real image. The next step is that we will crop the image, because the useful information is only in a small section of the recorded image. And to save computer memory and CPU time, it's rather advisable practice to crop the unwanted regions of your images before you start processing your data, because this can help you in achieving the results faster. So in order to do that, you have to make a rectangle around the useful information. So here in the middle you see the filter paper, and with this scroll bar at the bottom you can see subsequent images, and here is how the level of the water is rising. So you should make a rectangle and set up a region of interest around this filter paper. And if it wasn't a 2D measurement, then care should be taken that in all projection angles it should comprise the useful information. So if it is a tomography experiment, then in the different angles the object may have different sizes, appearance sizes, and those all have to be fitted fully into these regions of interest. And then you can simply discard the areas of the images which are not necessary for the further data processing. And this is already created for the entire stack. So if you make this cropping, then all 100 subsequent images will be cut to size and they will remain equal. So that's very important that the coordinates that you determine from the one pixel would be identical to the other. Now, so we have these shadow image, the beam image, and the dark image. And then they were already filtered, so they are ready to make correction. The information what we want to achieve is the shadow image minus dark image over open beam image minus dark image, because that's the net intensity where the proportion is related to the AR minus mu times thickness, and we look for either mu, this linear attenuation coefficient, or thickness, which is the geometrical characteristic of the sample. But in this case, the whole sample has equal thickness. So what you see in the picture is related to the change of the linear attenuation coefficient due to the presence of the boric acid water solution. So for this normalization, we have a plugin which I already included in this distribution file. It's called image referencing, and the data processing is very simple. You should specify the set of shadow images, the set of open beam images, and the set of dark beam images. And the program will do all the calculations for one mouse click, so very convenient. And then you see that something more useful would appear. So this transformation basically enhances the information content of the image for the human eye. And it's a little bit noisy, but you can already see the effect of the rising water level. The next step in the data evaluation would be to make a quantitative analysis of this waterfront propagation in time. So with this program, you can also record the coordinates of the mouse pointer, and the coordinate system starts at the top corner of the image, and so the waterfront is propagating upwards. So at some point it is useful to flip vertically the images, and then you have a better, more natural coordinate scale. Then we set up again a region of interest which covers fully the filter paper, but does not have any interference from the neighboring air. And then we also give a name of this region. And then the program will carry out the subsequent computing only on this given region, and the other outside regions will not be considered. And we will create a so-called plot profile. That means the program will start from here, and row by row it will make integration, so sum of the values, and it will plot it as a function of pixel vertical pixel position. And you can do this with the Control Alt and K hotkeys, or you can also make it from the menus. Then for simplicity, we create such a plot from every fifth of the images. But with a scripting functionality, basically you can make very easily scripts to digest all your images at once. And what is remarkable is that this the areas with and without water has such a sigmoid shape, and the inflection point of this sigmoid curve is shifting with the time. So you see that compared to this one, this and this are shifted towards higher pixel numbers. And this is the information that we want to extract from this experiment. Of course, we could do a peak fitting or a function fitting to this profile, but for simplicity, we just by eye find the middle of this sigmoid section. So checking one constant rate at this part and another one here, and then quickly calculate the average. And then we check wherever this average value is reached. And this will give us a pixel coordinate that you can read from the bottom axis, which will be dimension-like, distance-like quantity. And this will be used for the further processing. We have a Excel sheet which we prepared for the evaluation, where basically one needs to enter only these midpoint coordinates, and the Excel file will plot the diagrams for you. So you can always zoom into relevant regions of your plots. And see the level and the low level and the high level, and then you can find the middle point, and you can locate its position. And then for each frame which we evaluate, we put the pixel position into this table, and we will repeat it for every fifth frame. If you plot the pixel positions in the function of time, you will have a curve, but if you plot it against the square root of the time, then you will end up in a linear equation, and it can be physical-chemistry ways described with the adequate equation. So what we got from the experiment is really justified by the science, because this quantity is called sorptivity. It is defined as the measure of the capacity of the medium to absorb or dissolve liquid by capillary forces. And this sorptivity is used in the characterization of soils and pools construction materials, such as the bricks, stones, and concrete. And it was proven that if you do this horizontally, then this sorptivity is a proportionality constant with the square root of the time. While if it is vertical infiltration or water uptake, then there is an additional parameter called A1, and the equation can be extended to this form. And this is what we have seen from our experimental data. And this square root t dependence was plotted in the Excel file. And finally, this entire procedure was just for demonstration purposes. And this can be used in real life also for real materials, porous materials. And this was a example from porous building materials in Venice. And with this uptake experiment, you can separate nicely the stone matrix and the air voids, which can be filled up with air. And the segmented water content can be cross-checked with the numerical porosity analysis. And this way you can say something about the water uptake properties of your sample. Okay, so do you have any questions or comments to this section of the demonstration? I see no questions. So then we can proceed with the second part of the demonstration, which is volume rendering. So if you look at the camera, then here you find a child's toy, which gives some casted object, and inside there is a surprise for the kids. And this toy will be used as a demonstration for our today's exercise. And of course, you can dig out the content only destructively. So you have to ruin the object in order to access what's inside. But as we are curious, we want to do it non-destructively. So Neutron and or X-ray imaging can be used to reveal the contents of such a hybrid object without any destruction. So this is the outcome. We can use several modalities, several different radiation types in order to visualize such an object. If we are interested in the surface only, then we can do three-dimensional structured light optical scanning to acquire skin of the image. But it will not show us what is inside. For inside the content, you need a volumetric imaging method like tomography. So we record several hundreds of projections, and we make image processing, a reconstruction, where these projections are converted to slices. So these are horizontal cuts of the object from the bottom to the top. And then we can stack them together, one above the other, in order to create this three-dimensional volumetric data set. And then, based on the grayscale values, the materials can be segmented. So segmentation is a procedure where we separate different materials based on their ability to interact with the particle beam. So in this case, the dinosaur has different attenuation coefficient than the stone, so they can be very nicely separated. So this data set can be cut into two halves. That is the dino half and the stone remaining stone half. And this is exactly what is done in the industry, called reverse engineering. So you try to reproduce an object without knowing anything about it. So often they don't have the blueprints. Often they have no knowledge about the internal structure. And by reverse engineering, one can recreate the object. And in this procedure, tomography could be a very useful contributor in the data processing chain. And once we have this data, we can do some kind of an engineering analysis about the dinosaurs. So for instance, what is the maximum thickness of river water that it can swim through? And eventually, we can even use 3D printing technology to recreate the dinosaur, which is still inside of our intact stone. And that would be reverse engineering. So what was the features of three-dimensional data visualization? This is called volume rendering. In this functionality, we can nicely present the object in 3D. We can do unlimited rotations. We can do geometrical cuts with regular shaped objects like plates or boxes. We can differentiate between materials based on their attenuation coefficients. This is called segmentation. And we can show or hide relevant materials of the composite object. And we can extract the relevant components to a separate data set. We can assign different colors to certain grayscale ranges. So some materials can be highlighted. We can load more than one data set, even if they were recorded separately, and we can align them to a common coordinated framework. And they can be then jointly visualized and jointly numerically evaluated. Because in these programs, not only visualization is possible, but there are quantitative analysis features also, like pore size distribution measurement or surface determination, casting defects analysis, and so on and so on. So all these numerical data processing can be done on one or more data sets. We can also create outputs for computer-aided design. So the tomography data can be later used in comparison for the CAD data, or we can use them in 3D printing procedures. So if you compare directly the surfaces from tomograms to the blueprints of the original part, then you can see manufacturing defects easily. So there is deviation from the plan, and you can correct the procedure accordingly. And finally, these programs comprise also very impressive movie creating features. So you can record also motions within your sample. And this is how such program look like. Here is a three-dimensional view, and these are horizontal and vertical cuts of the object. Here you see the data tree. So here find the data sets one by one. And this is the grayscale histogram, where you can adjust the visibility of certain grayscale ranges, so certain materials actually. So if you move one plane, then this cross section is changing. So this way you can hide the stone and just keep the dyno. You can freely rotate it in the 3D space. You can create a clipping box, so you can geometrically cut certain part of the object away and reveal what is inside. So now you have only a half of the dinosaur. And if you manage to segment one material, we can make a so-called surface analysis that will make the volumetric information, so voxels, will be transferred to triangles. So the surface of this object will be represented by tiny triangles, and these will be used for CAD or 3D printing applications. We can also set such an object as a region of interest, and then we can apply some highlighting or coloring. If we enable ROI-dependent render settings, then not all the object will be shown in grayscale, but we can set certain parts of the object, like this one, with a color scheme, and then we have already a golden dinosaur. I will show you finally some videos which we rendered. This is a lock of a travel case, and inside you see very nicely the internal mechanism, and even it is possible to figure out what is the combination to open. As I mentioned, it is also possible to merge several datasets into one image or one dataset. And the next one will highlight this one. So this movie was made of two distinct datasets. One was recorded by neutrons, and the other one was recorded by X-rays. And these two things were numerically aligned to each other, and then they are jointly visualized. The blue and the red segments will represent the information from either X-rays or neutrons. You can show them together or separately. Okay, so that was the demonstration. Do you have questions to this part? Please, any questions, comments? So with this image processing, you can spend ages to tune the visual appearance of your data. So such a very impressive and detailed visualization can be done using these programs if you have plenty of time to elaborate the visualization. Or the other fancy trick is that you can make certain parts transparent with this. You can reveal what's inside. This is a bird. One strange thing is that you can even do geometrical manipulations, so virtually unroll such a roll. So you see that there is an engraved script on this, which is of course not possible to read without destroying the object. But with image processing, you can flatten these curved surfaces and make this reading available for study. Yes, how long does it take to acquire an image? So one image projection, I mean, takes a few seconds, so between 1 second and 10 seconds, I would say. And we typically acquire 600 of these projections for a three-dimensional tomography. So within a few hours' time, we can record data. Yes, of course, we can export all these data from ImageJ either via the clipboard, or you can save it as a comma-separated value file, and then from origin or whatever Igor fitting programs you prefer, you can further process the data. So it's indeed possible. Once you flatten this out, then you can really read the script. Another case study was done with our data set. Here you see pottery, fragmented pottery, and X-ray and neutron imaging were made. And you can make numerical distribution analysis, so you can check the grayscale values and see where are the different hotspots. You can merge the two data sets, as I mentioned already. And you can achieve almost exact visualization. You can see very nicely the gluing material in between the fragments, which are shown very nicely by neutrons and which are absent in the X-ray imaging data set. Then you can also highlight it. So if you segment it by grayscale and apply some false coloring to this material, then you can highlight the presence of these gluing materials. You can even create a surface determination piece by piece, so fragments can be digitally created. Porosity analysis can be done numerically. So voids and the cracks can be identified. Inclusions can be also identified. And hole thickness analysis can be also made. One question from the chat, are there any restrictions on the choice of material samples? Basically, the only requirement is that we need to be able to transilluminate the object. At least 10% of the beam should pass through the sample. And each material has different ability to attenuate the neutron beam. So for each sample matrix, the size of the sample can be different. So if you take an example of water containing sample, there 1 or 2 centimeter of water can already absorb completely the neutron beam. So the maximum size for those samples are in a range of few centimeters. The other end, if you consider aluminum or silicon or Teflon, the maximum size of the object can be up to 10-20 centimeter because they are much more transparent to neutrons. The other requirement is that the object shall completely fit into the field of view at all rotation angles. And if this is not possible using one run, then we should make 2 or more runs and put together the projections before the tomographic treatment. The other thing which one might need to consider is that the activation. So there are certain materials which are activated by the neutrons. So the most typical examples are silver and gold. And these objects have a maximum exposure time, how long they can sit in the beamline in order to avoid the excess activation. And this we already pre-calculate and we plan the experiment accordingly. But for most of the cases, the experiment is quite routine, and neutrons have good penetration power, so they can transilluminate samples which are impossible by X-rays. And with neutrons, you have much fewer imaging artifacts because it can create better quality images, and less process after processing is required to correct for these artifacts. Like beam hardening is an effect typical to X-rays. That means at the surface of the object, the average energy of X-ray is lower than in the middle parts, because lower energy softer X-rays are easier to absorb in the near surface layers. So only more energetic X-rays can make their way to the deep layers of the sample. And this is called beam hardening. And if you know the material property, this can be numerically corrected for, but only if the sample consists of basically one material. And as soon as you have multiple materials with multiple attenuation coefficients, then this very simple correction does not work anymore. And that's why it should be better avoided. And in case of neutrons, this effect is also present, but much less abundant and much less serious. So in many cases, we can achieve satisfactory results even if X-ray would fail. Do you have any questions? To finish this demonstration, I would like to view a few more videos for you. So this is the so-called structured light optical scanning, which can acquire the surface of an object and with photorealistic skin. And this surface data set can be merged together with the volumetric data we record with tomography. So you can improve the quality of your images by adding this visually rich skin. This is a movie about a ball bearing made of steel, and the question in this experiment was to find out the reason of the malfunction. So this is called in industrial practice root cause analysis. And in order to achieve a direct comparison, we imaged under the same conditions a new one and a damaged one from the same bearing model. As shown in this photograph. They are bound together with these Teflon things. Teflon is very transparent to neutrons, so they are very nicely used for fixing the object or using as a placeholder. It has no hydrogen inside, so does not scatter the neutrons too much. Here you see that in the top view, where the new item is shown, you see these white areas, which is the lubricant, the grease, and it's distributed all over. And this bottom region, you see many cracks already, and much fewer places where this grease is present. So neutrons have the ability to visualize not only metallic components but also organic components via their hydrogen content. And in such an exercise where not only one kind of material should be shown, but metallic and the non-metallic part should be simultaneously visualized, then this neutron technique could be well applicable. We have here a neutron imaging experiment of a large electromotor rotor that's going to be used in advanced electric cars, and it's rather bulky. So the diameter of this thing is kind of 10 centimeter in size. And the goal would be to find manufacturing defects, voids, and this time we used not low energy neutrons, but medium energy neutrons. They have higher penetration power, so even such bulky objects can be transilluminated, but at the same time the resolution is somewhat worse. So we can always select the adequate neutron energy range for the given problem. Because from milli electron volt to mega electron volt, we have neutrons available. Then you can do the segmentation, and afterwards you can make this very nice exploded view where the different parts can be separately shown. The cutting place can also be non-parallel to the main axis. You can use any defined plane to cut to the internal details. The next example is a fish bone that's embedded in a piece of stone. And of course, this had to be studied in its full scale. And these white spots, which are inside the stone, are the belongings of this ancient fish. So here you see some bones of the fish. You can also make a dynamic imaging. That means the sorry for this contact issue. So here is it's a very dense liquid with high viscosity, and we just wanted to see how far it can flow down on a curved surface. And you can see the timestamp on the images. So the frame rate is in the order of fractions of seconds. So if I write, it is 100 milliseconds. And then you see how this very viscous material is flowing down. And this is a benchmark study for numerical computation, because the flow of such liquid you can also characterize by CFD calculations, computer fluid dynamics, also considering several factors like gravity and viscosity. And this was a benchmark data set for such calculations.